Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
All right, let's make a start. Okay, so sorry we're all over the other side of the room today, and I'm kind of stuck on this side because that's where the keyboard is. So I apologise for that. Apparently, if we're very lucky, we'll get another visit from the AV guy, and he's going to come and kneel down here and open up cabinets and do something. Maybe, I don't know. And then maybe that'll start working. So anyway, do you guys have any other lectures in this room? Yeah? Does it never work? Yeah, it works, just not for me. Oh well, that's a bit sad. Oh well, not to worry. Okay, so talking about densities, we got through most of that yesterday, and we talked about all the sorts of different densities that you can produce with different choices of window or kernel and different choices of window width. Okay, so we're gonna have another quick look at that, and then we're going to have a look back at histograms just to compare. And then we're going to move on and talk about a question that comes up whenever you look at densities. All right, so let's first of all just have a look at a density with the intermediate stars. And again, I'll use some of the commands that are here in the class data thing. Okay, there we go. So this is a density. So this is using the cosine kernel. As you can see, not a lot of difference between this and the normal or Gaussian kernel. We've got a little bump out here, and we've got a big bump here. And we talked about how to describe this distribution yesterday, right, in terms of its shape. And you know, most people would agree that it's skewed. The bump is over to the right, the tail is to the left, so it's left skewed. And there's a question around whether or not this little bump here is real. Does it reflect reality, or is it an outlier, or what? And we don't know the answer to that question, okay? But it's a question that occurs once we look at that. Now, what I want to show you is how you can use different window widths and put them all on the same graph, okay? So this is just using the default window width, which is pretty good. But I'm going to go back and do it, and I'm going to put in a specific window width. I'm going to make the window width a little bit too small. So width equals, say, maybe 10. Okay, type equals L. So this is a cosine kernel with a window width that's a little bit too small. You guys might want to sit on this other side here, because this one isn't working. Oh, something's happening, but it might work. We don't know yet. It's a mystery. That one over there is working. So, no, it's not working. There you go. Cool. All right, now what I'm going to do is I'm going to add to this plot new densities with different window widths. This is really just to show you how you add to an existing plot. Now, the command is really kind of simple. It's lines, okay? You go lines, density, well, something's happening, of inter. I tell you, it's a joy being in this room. Window equals C, so we'll use the same kernel. Okay, and now what we're going to do is we're going to go width equals, say, 50, so a bit higher. All right, but now I'm going to go LTY equals 2. So LTY stands for line type. So instead of getting a solid line, this time I'm going to get a dotted line. Okay, so you can see a dotted line has appeared here, and it tracks along, and it's a bigger window width, so you're getting fewer bumps, but you can see that it's on the same plot. So this is good for comparing things. I don't have to use different line types. I can use different colours if I wanted to. So I could go and add another one of these, maybe with width equal 150. Instead of using line type 2, I could use colour equals. You can use numbers, or you can name the colour. So I'm going to say orange because it's a nice colour. And you can see there's the density with window width equal to 150. So the main reason to show you this today is just to show you how you can overlay different densities on the same plot. Now these are all densities of the same object, all densities of the same stars. Later on you might want to put densities of different objects on the same plot. Same idea. You start with an initial plot and then you use the lines command to add things to that plot. And then you've got flexibility around how those things look. So, for example, you can have different line types, you can have different colours, and you could, or both, right? You could have different line type and different colour. So I could add another line to this plot. Let's make it stupidly overfit, so 1500. I'll have a different colour, so let's make it a green. And I can have line type equals 3, which will be a dashed line. There you go. Now, it's not very visible. But if you look at it, if you're up close enough to this, you'd see it's sort of like a dotted line. So the first one's a dashed line. The dashes are a little bit longer. This is a dotted line. Okay? So you can do this kind of thing pretty easily. Now, the other thing I'm going to point out about densities before we move on is the scale here is not all that meaningful, right? What do we know about probability densities? What's the area under the curve? Yeah, so the area under the curve has to be 1. So the scale here is such that the area under the curve is 1. So it's really not meaningful in any sense. When we did histograms, you didn't get that, you got the count, right? Now you can force histograms to give you probabilities by using the probability equals true option in the histogram, and that would produce a histogram on a density scale. And then if you wanted to, you could put a histogram down on the page and then overlay a density on top. Now, I don't recommend doing that. I don't see any point in doing that, but you could do that, okay, if you wanted to. So, for example, I could go hist of inter probability equals true. That produces a histogram on the density scale. So the area under this is 1. You can see these numbers are a lot smaller. They're no longer counts. And then I could go through and put the density on top of it. And you can see it lies over the top pretty well. And that's because these are now on the same scale. If you just did the histogram without probability equals true and then you line the density on top, you'd probably look at it and go, nothing changed, because what happens is the density is way down here. It's squashed right to the bottom because the scale is so different, okay? Let me show you that. Hist inter probability equals true. Let's not put the probability equals true. Let's put it on the count scale. Now let's put the density on. And you can see, I made it orange so you can see it. It's right at the bottom here. It's just flat. Now, it's not really flat. You know it bounces around, but the scale is so small, it's pretty flat. Okay? So you can overlay things. Now, let's think about this from a graphical perspective. I think there are some sort of good general rules around this. Overlaying things is good because it initiates a comparison, right? If you've got two lines on a plot, your mind is immediately drawn to the question of comparing them, right? How are they different? How are they the same? And what does that mean? And so overlaying stuff is a good strategy if you want to initiate that kind of comparison. But be careful, okay? I have seen, and this is perhaps advice for the assignment, perhaps it's not. So if you've got to compare 4 or 5 different things, or 8 things, for example, if you have 8 lines on a plot, that much more resembles a bowl of spaghetti than a useful graphic, okay? It's just lines everywhere. You're looking at it, you're going, I don't know what, and you can put legends on and do all sorts of stuff, but you know, in the end, you're defeating yourself, right? Legends are great, but I'll tell you why they don't particularly work well. Let's go back and I'll put a legend on a plot here. So we'll go back to the original density with the stupid window width. We'll add a couple of lines, okay? I'll add one more. So these are just the commands I did before, so nothing really new. Okay. And then I might look at that and go, okay, well that's cool. I've got 3 lines on the plot. I want to compare them, but I don't know what each one is. Well, that's not good. So there are a couple of ways I can do that. I can put a legend on the plot. the command is legend. Now I want to click where I want it, so I'm going to go legend locator 1. So locator 1 is a function that basically where I click, it'll put stuff. Okay, locator 1. And then the text might be, let's see, what have we got? LTY equals C, sorry, I need the legend text. Oh, fireys are coming. Boy, it's fun lecturing in this room, isn't it? The text is going to be C, what have we got? Width equals, what was it, 10. So I'm just putting some text down. Width equals 150 and width equals 50. Okay, so that's the text that I want to put in. Oh, I've got too many quotes here. Something's going on. Okay, comma, and then I want the different line types. I've got 3 different line types. LTY equals C. The first line type was a regular line. So was the second one. It was just a different colour. And the third one was line type 2. And then colour equals C. Well, we got black, which is 1. Orange, which I don't know. I have to use black. Orange. See if it'll work. Here we go. Maybe it'll work. So the normal distribution is special, and we can all agree on where the middle of the distribution is, okay? But when you've got a skewed distribution like we do here, and it's about to appear, you watch, the question of where the distribution is located, oh, that's good. The question of where the distribution is located is kind of a more difficult one, right? So I've got this skewed distribution, which you can't see. Is that any of those TVs working? Is that working? No. Okay. How exciting. All right, let me just type something.
Try switching tabs.
Sorry?
Try switching tabs or going to the desktop.
Well, yeah, okay. That's a good idea. Good thinking. Well, there you go. You should work in IT. That's awesome. All right, well, let's cut to the chase a bit since we're bleeding time here. I'm going to go and just do this density again. Okay, it's a bit over the top. Let's try 200. Width is 200. Okay. I mean, just to show you how to do legend. Legend locator 1. I've only got one line on it. Text is C, one line. LTY equals 1. Okay, so see what happens. It sits there waiting for me. This changes to a crosshair. As soon as I click it, it'll put the legend wherever I click it, right? So there it goes. I can put another one on. It really will put it wherever I click, right? So be careful where you click. Generally speaking, up here's fine. By the way, what do I think about legends? I don't really like them, right? I'll tell you why. Because they're up here, and the rest of the stuff you're talking about is down here, and so you've got to look back and forth, back and forth. It's really not good. If I had a choice, I'd probably just do this. I'd probably put the thing on the plot. I'd go text locator 1, and then whatever I want to call it. So, right, and it waits, and it'll put the text wherever I say. And I think putting text, well, it centres it. That wasn't necessarily the best choice. Let's try that again and see if I can get it to go off centre a bit. Yeah. So you can put it where you want it. And then if it's next to the line, right, it's going to be better than if it's way up in the corner. So you can label things directly that way, although it's a bit sensitive to where you click it.
Can we remove the one that we don't like?
No. No, you have to do it over. So once something's on a plot, that's it. Once something's on a plot, that's it. So you have to kind of get it right. Okay? But, you know, life's like that, right? Life's like that. To relate it back to our previous discussion, there has been a few times in my life where I've had a flat tyre, right? Half hour later, I fixed it. I go to pump it up. The bloody thing has it was a pinch flat and there was a second hole. And I got to do the whole thing again, right? Yeah. Luckily, that didn't happen this morning. Otherwise, we'd be having our lecture in Yarralumla, in the mud. Huh? Lovely. All right, okay, cool. Back to talking about what. Where's this distribution located? Where's this distribution located? Who wants to? Okay, I'm going to run my finger. I'm going to sit down here. I'm going to run my finger along. You tell me where to stop, where the distribution is located. Well, that's not what I asked you to do. I'm nowhere near zero yet. All right, no, 0.
Stop.
Yeah, you reckon? Okay, cool. Oh, very good. All right. What do you reckon that is? Is that the mean? Mean is minus 15. What's the median? 5.5. So the median's probably a better call for this, right? Okay, so that's cool. Wouldn't it be nicer if we didn't have this sort of question about whether to use the mean or the median? Wouldn't it be nicer if we could just use a single number and everyone could agree on it? Because, you know, a lot of people are going to use the mean no matter what because people love means. And then, you know, people who've done a bit of statistics will go, oh, but you should use the median. But, yeah, you know, there's that disagreement. Wouldn't it be nice if this was a symmetric distribution, right? Now, you can transform data to make it more close to symmetric, and that's something people often do. And there are a couple of reasons people do that. people often transform things to normality for two reasons. One is to gain symmetry. So in other words, be able to say unambiguously where the centre is and be able to estimate the spread. The normal distribution is a pretty special distribution. If you know two numbers, you know everything, right? You know where the middle is and you know how spread apart it is. That's it, right? Whereas if you have a distribution that's skewed, you need at least three numbers. You need a location, you need something to deal with the spread, and then you need something that deals with that skewness, you know, left to right ratio kind of thing, okay? So the normal distribution's kind of special, and so it very often comes up as to asking the question, is my data normal? There's another reason it's special, and that is that almost all of classical inference, all those t-tests that you've learned about, all those f-tests that you've learned about, they only actually work if your data is normal, right? So in other words, if I was doing t-tests based on this data, I'd be in a little bit of a world of pain because the t-test, well, it doesn't fail utterly, but it's not going to give me exactly what I'm looking for, okay? And, you know, just so, and people say, well, why are you doing t-tests? Well, already I've had emails from people saying, I've been looking at the assignment, the keen people, looking at the assignment, can I do t-tests if I want? To which my response is, you do whatever you want. Not up to me, right? But, you know, it is something inside us, if you've done enough statistics, to want to do tests, to want to do, you know, confidence intervals. The point of this course, of course, is to draw pictures. So that's principally what I want you to do. But if you want to use tests, that's fine. Just remember, if you want to use tests, you better be sure your data is pretty close to normal. Otherwise, your test isn't really right. Okay? So a question that comes up eternally is my data normal? Okay? So how do you answer that question? So what I'm going to do is I'm going to generate some data that is normal. Okay? We're going to have a look at it. So we're going to have a look. We're going to generate a lot of it. We're going to generate 1,000 random normals with mean 0 and spread 1. Okay? And I can look at this 9 ways till Sunday. I can do a histogram. So question, is that normal? Yeah, looks all right. Histograms don't really do justice to the normal distribution because they're way too blocky. So I might be better off doing a density. So plot density. Oh, something's wrong with my fingers. I always type density. Density x, and now window equals, we'll choose a Gaussian window. And width, well, what width should we use? Let's just see what the default does. And then comma type equals L. That's a lowercase l. Okay, that's what the density looks like for this particular data. A bit bumpy, but so that's the default window width. Now here's a question. How do I choose the window width if I want to do a little bit better? Remember what I said the other day. Take the range of the data. Think about that. So here this data set goes from about -4 up to about +3. Okay, it's a range of about 7. A reasonably good place to start is to take that range and use maybe 1/3 of the range. And that's just a rule of thumb. So don't email me saying what's the theory behind that. There's no theory behind that. This is really just something that generally works. For every rule that generally works, you will be able to find cases where it fails. Okay? So it's just a rule of thumb to just get you started. And then you mess around with it if it doesn't work properly, right? So I'm going to try a window width of, what's 7 divided by 3 is about 2. So I'm going to try width as about maybe 2.5, just to give us a bit more. So width equals 2.5. And you can see that's a little bit smoother. Let's see if I change it down to 2. So basically we're just going to try a few things. Doesn't make much difference. Okay, so width equals 2 is probably pretty good. And you can see that that thing here looks like a normal distribution, right? Now, one of the things that happens when you've taught statistics for 30 years is you can draw a normal distribution freehand, right? So I can do that without even thinking, a normal distribution, easy. And you guys probably can do that too. It's not really that much of a specialised skill. But having said that, you know, if I say to you, is that bell shape, pretty much everyone's going to say, yes, it is, right? So everyone think that's bell shape? Yeah? Yeah? Cool. Okay. All right, now I'm going to generate data that's not normal, right? You're going to watch me do it. So you're going to know it's not normal. So I'm going to generate data that has a t-distribution. I'm going to generate 1,000 of them. I'm going to give it degrees of freedom 10, right? So a t-distribution with 10 degrees of freedom. And I'm going to do density of that. There it is. Is that bell-shaped? Somewhat. Looks bell-shaped. Yeah, it looks bell-shaped, right? But we know that's not normal data. So how does the t-distribution compare to a normal distribution? Who remembers?
It's nearly no.
Well, it's got heavier tails, right? Heavier tails. Symmetric, so it's got some features in common with the normal. It's symmetric, but it's got heavier tails, okay? And you can't tell when you look at that. Because when you look at that, it looks bell-shaped. Everyone's going to sit here and say it's bell-shaped, okay? Now, the person who said somewhat is hedging their bets because their eyes said, yes, it is, but then they watch me generate the data, which says, no, it's not, and so they're having a bet each way. That's fair enough. But that data is not normal. You watched me generate it. There's a lot of data, right? 1,000 data points. And yet you get a picture that pretty much everyone in the room will sit and look and say, well, that's bell-shaped, okay? Now, there's a good reason for that. What does bell-shaped mean? And you've got this sort of broad conception of what bell-shaped means, but it's pretty much the Monty Python definition of a brontosaurus. You remember that sketch? The brontosaurus? Small on one end, big in the middle, small on the other. That's what a brontosaurus looks like. That also describes a bell curve, right? Small on one end, big in the middle, small on the other end. So most people have very simple models for what bell shape means in their heads. But if I said to you, draw a bell shape, well, you'd draw something that looked like this, and it might or might not be bell-shaped. So in other words, you making a comparison between this shape here and a bell, a perfect bell, is something that you're just not trained to do. Okay? Now, there are things you are good at, and you've been good at them since birth, right? For instance, if I show you a pattern and I ask you whether it's a straight line or not, pretty much all of you know how to answer that question, right? Because you're good at noticing deviations from straight lines, right? You're also good at noticing whether things are parallel or not. Have you ever walked into a room where there's a picture hung crooked and you notice it right away? It's just one of those things you notice right away because it just like, oh no, that's not right, you know? So you're good at knowing whether a circle looks like a circle. And even small deviations from circular you'll pick up. But you're not good at bell curves. So what we're going to do is we're going to talk about a plot that converts this kind of decision process, you know, me asking you the question, is this bell-shaped, and you having a response which is generally going to be, what do I... Well, your response is basically considers, what does he want me to say? He probably wants me to say yes, so I'm going to say yes, right? But, you know, you've sort of bypassed any of your actual will in that question. Whereas if I ask you if something's a straight line, you might think I want to say yes, but if it doesn't look like a straight line, you're going to say no, because your eyes are going to tell you that. So here's a plot. I'm going to go back and regenerate the normal data, the data that's actually normal. Okay, here's a plot. Called the QQ plot, which takes the data, tries to convert it to essentially normal, and then plots it against a normal. Okay? And it says, what do I get? What's that matchup look like? Okay? So this should look like a straight line. This should look like a straight line. Who reckons this looks like a straight line? Pretty good, right? You usually get a little bit of problems at the edges because normals have outliers too, right? So you can ignore one or two points at the edges, but as long as it looks mainly like a straight line, then you can sort of see that the data is going to be normal. So let's generate some t data. Just going to take the degrees of freedom down a little bit. Is that a straight line? You can kind of say now it's not, because it looks straight for a while, but then stuff starts to happen, right? This tail starts to move up faster, and this tail starts to move down faster. And the straight line would take you there, right? So that's not a straight line. So I've shown you two data sets now. One that I know is normal because I generated it as normal, and one that I know is not normal, it's heavy-tailed. And when you look at the densities, you go, yeah, they're both bell-shaped, right? Because you just can't tell. They both look bell-shaped. But now I've shown you an alternative plot which converts that decision from is this shape a bell shape to is this shape a straight line. Much easier decision for you to make visually, okay? And now you can actually say, oh, trick me once, shame on you. Trick me twice, shame on me, because you showed us something that looked bell-shaped, but you know what? It's not normal, because look at that. That tail there is definitely heavier, right? It's moving away from the centre faster than a normal, okay? So these things are called QQ plots. Now, you might have seen QQ plots before. Probably you have. They're covered in most undergraduate first-year stats courses. But they're generally treated a bit mysteriously. You are told this is a QQ plot. There's a command that does it, and this is how you use it. But you're not really told how it works. So I'm going to try and tell you how it works. So let's look at the plot in a little bit more detail. On the bottom, on this axis, it says theoretical quantiles. Okay. On this axis, it says sample quantiles. So this is your data axis. Your y-axis is your data axis. And your x-axis is a standard normal. Right? So here's how they construct a QQ plot. They take the data and they sort it from smallest to largest. Okay? Then they construct theoretical values of a normal. If you had 1,000 actual normals and you asked, what is the smallest one going to be? They create those. For smallest, second smallest, third smallest, right up to, if we had 1,000, 1,000th, the largest. Okay? Now, if your data is normal, these things should match up on a straight line. Okay? And so you plot one against the other, and if you see a straight line, then it's telling you that your data, when sorted, looks like the sorted data from a normal. Now, those second things are called normal scores. And there's a formula for them, okay, which R knows. The formula is pretty simple, but I don't think it's necessary for us to talk about it. But what I want to do is I want to take you through how these things work, okay, and just show you a few examples, and then we'll draw some using data that I construct, okay? So let's do that. Now, to do that, I'm going to use this document camera. So let's see if I can get that to work. Life's an adventure in this room. Maybe it'll work, maybe it won't. Uh-oh. Uh-oh. Hello? Well, this is discouraging. All right, well, if at first you don't succeed, try again. Come on. What's the roof look like? Well, that's just not going to work, is it? So, we'll get that back, refresh. Okay. All right, well, we'll just have to do without that. So, have to do it with hand puppets. Eh? All right, this is what we've got to imagine, okay? So rather than drawing it, I'm going to have to do it on the screen and just point. And I'll try and point with the mouse so that people who are watching at home can listen. Okay, so if you put your mouse here and you put it around the middle, right? Well, I can put lines on this. So I can put an AB line that's horizontal at 0, and I can put an AB line that's vertical at 0. So I'm just sort of creating a middle for my plot here. Okay, so that's the middle. And then as you move away from the middle, right, you think about the distance the data point is from the middle. Okay, so let's, and I'm also going to put another line on this plot, QQ line of x, which is the straight line that I wanted. Okay, so there's the straight line that I wanted. All right, so what does this data look like? Well, when you're near the middle, it's all good, right? Because the distance from the middle is on that line, right? So the distance from the middle for your data is that little distance there, and it should be on the line if your data is normal. So it's about the right distance from middle. When I'm out in the tail, this point here, for example, it's a long way further from the middle. It's this far from the middle, and it should be only this far from the middle. See where my mouse is going? So it's supposed to only be up to the line. Okay? So it's supposed to be this far from middle, but instead it's a lot further from the middle. Okay? So in other words, I've got a heavy tail on this side, right? My data's consistently further away from the middle than it should be. It should only be out to here, right, this distance, but it's up a bit further. So as I move out into the tails, I'm getting consistently heavy tail on this side. So on the right side, I've got a heavy tail. What about the left side? Same sort of thing, right? This point here, that's a lot further from the middle than it was meant to be. It's supposed to be up here on the line. Instead, it's down here. Okay? So this tailing down is telling me that my data is further away from the middle than I expected it to be. I expected it to be on the line. Okay? So I've got a heavy tail on the right-hand side. I've got a heavy tail on the left-hand side. And it looks pretty symmetric, right? So heavy tail on each side. So this is telling me my distribution's heavy-tailed. Okay? So when I see this S shape, that's the sign of a heavy-tailed distribution. Okay? Easy to remember. This is what the plumbing behind your toilet looks like. Right? It goes down and then it shallows out and then it goes down again. In plumbing that's called a trap. Why do I tell you that? Well, if your data's heavy-tailed, it generally means it's not normal and you've got essentially contamination away from centre, which means all of your tests are going to have significance that's not as good as you expect, and your analysis is going to go down the toilet. Right? That's how I remember it. Heavy tail is the S like the toilet. Okay? All right, let's put on some data that we know is skewed. Okay? So what's a skewed distribution? Chi-squared? Chi-squared distribution is skewed, right? So let's create some skewed data. So R chi-squared, I'm not typing in the right spot, let's go back over here. X equals R chi-squared. I'm going to generate 1,000 of them, okay? And I'm going to give it a degrees of freedom of 3. It's going to be pretty skewed. So I'm generating 1,000 chi-squared 3s. Okay? Let's put the QQ plot of that on the screen. Okay? Notice? So, well, let me ask you the obvious question first. Is that a straight line? No, no. It's curved, right? It's curved. So skewed distributions have curved QQ plots. And it's curved facing up, right? Because the skewness is on the up side. It's on the right. Okay? How do you know? Let's have a look at the histogram. The histogram of X is... So that's a very skewed distribution. It's got a big bump on the left, big tail on the right, skewed to the right. QQ plot, curved, curved up, right? Up is right. Okay. Now let's put those crosshairs on it again. So let's go AB line. So on a vertical line at 0. So that's the middle of the theoretical distribution. What's the middle of the chi-square distribution? Well, it's going to be roughly equal to the degrees of freedom. It's going to be roughly equal to 3. So I'm going to go AB line, H equals 3. That should go close to the middle. Remember, there's that whole mean-median thing going on, so I'm using the mean, but it's close enough. So this is the middle of each of the two distributions. So let's put the line on the plot. Let's put QQ line of X on. There's the line it should be on, so it's doing that. Okay? Now, right-hand tail. The points are further away from the middle, right? So they're up here and they should be down here. So you've got a heavy tail on the right-hand tail, okay? Heavy tail on the right-hand side. Everyone see that? Okay. What about the left-hand side? Points are supposed to be on the line. Well, the line's down here, right? Points are supposed to be on the line, but they're not. They're closer to the middle, right? They're closer to the middle than they would be if they were on the line, because the middle is up here. They're closer to the middle. So they're smushed up on the left-hand tail, right? So I've got a short tail on the left, long tail on the right. That's a skewed distribution, and it's skewed to the right. So whenever you see this shape, you can tell what's going on. Right-hand tail's heavy, left-hand tail is short, okay? And that's what the QQ plot looks like. Now, if your skewness is in the other direction, you turn it upside down. Easy to generate. All I've got to do is create a chi-squared that goes in the other direction. Just put a negative sign in front of it, you'll get exactly that. Okay? So if it's skewed to the left, curved again, curve goes down, or left, skewed left, okay? And there you have it. So, heavy tail, you get that S shape, like the toilet, back of the toilet bowl, right? Skewed to the left, curved down. Skewed to the right, curved up. Okay? All right, now it's time for some fun. Let's generate some data. You can watch me do it. X is uniform. I'll generate 1,000 random uniforms. So it's like dice rolls. Okay? So, what's the histogram of X going to look like? It's like a row of British teeth. No, it's pretty flat. Pretty flat. Okay. Here's my question to you. Okay, well, let me ask a series of questions. Is it bell-shaped? No. Good. Pass. Okay. Here's my next question. Is it symmetric? Yes. Right? So middle, left and right, basically the same. Okay. So yes. Not bell-shaped. Yes, it's symmetric. Okay. Who thinks it's heavy-tailed? Who thinks it's heavy-tailed? Nice and high if you think that. You'll either be right or wrong. Okay. Who thinks it's light-tailed? This is like Parliament. 150 people sitting there. The vote wins 3-0. Who has no opinion?
I think there's no tails.
Well, but no tail would be light, right? So if you think, who thinks no tails? That's light. So no, we've got a few votes for no tails. So let's do that again. Heavy tails? Okay. Light tails? It's a tie. And there's a lot of people who still have no opinion. You've got to have an opinion, folks. Okay, so you're mixed. You don't know, in other words. As a group, we don't know. Okay. How are we going to tell? Let's have a look. That's the QQ plot. Okay? That's the QQ plot. Put a horizontal line at a half, because that's the middle of 0, 1. Put a vertical line at 0. Oh, man, got to type it properly. And a QQ line. So there's the crosshairs and the line. Okay, what's going on in the left-hand tail? Left-hand tail. Points are closer to the middle than you expected them to be. You expect them to be on the line. That's down here. They're much closer to the middle. So you've got a light tail on the left. Same thing's going on the right. You've got a light tail on the right. It's light-tailed. So this is another S shape, but it's probably better than the heavy-tailed, right? Heavy-tailed generally means contaminated, more error than you expect. Light-tailed is less error than you'd expect. That's better. That's good. That's like the S on Superman's chest. You know Superman? Yeah? S. Right? So when you see an S shape, you know that it's got different tails to a normal, either light or heavy. Heavy's bad, so that's like your analysis is going down the toilet, so that's down, down, flat, down, right? This one's better, so it's like Superman. That's how you remember. Easy to remember, right? You're going, why is he telling us stupid things? Well, try and remember it if you don't have little hints that help you do that sort of thing, right? Because, a year from now, when I'm not around to tell you, you go looking at it, you go, well, it's an S shape, but I forget what that means. Right? But you won't forget now because you'll think toilet or Superman. Okay. All right. So that's that. All right. Now, the next bit of fun is this. So I'm going to what am I going to do? Just sit there for a second. Just going to do something over here. So you don't get to see what I typed. I've just generated some data, okay? And here's the QQ plot. So have a look at that. Looks like what? Staircase, yeah? What's histogram look like? Bell-shaped. Uh-oh, what's going on? Why does it look like that? Who can tell me? Who knows? Sorry? Close. Yeah. Discrete. Close again. So, no. Getting further away. That's okay. So, I first of all generated normal data. Okay? That's why I got the bell-shaped. Then I rounded it. Right? I stripped off everything after the decimal point. When you round data, it sucks it into the integers, right? So these little flat bits are, remember this is the data axis, they just line up with integers, okay? So whenever you have rounded data, whether the data is normal or not, you get steps, okay? So whenever you see steps in a QQ plot, it's because you've got rounded data, okay? So I'll show you. That's where I generated the data using random normal, okay? I then rounded it, just went round, and QQ norm. Okay? So that's what rounded data does. Gives you steps. Now if I put a QQ line on that, most of you would still probably say, what's going on? Oh my God. There. Most of you would probably say, well, look, it sticks pretty close to the straight line. It's just got steps. Right? So you still think it looks pretty normal. If you did a density of it, it would look normal. But the steps tell you it's been rounded. So that's something that's useful to know. All right. You're in the dark again. All right, it's a QQ plot. What's this tell you?
More data in the center.
Well, there's data everywhere, right? Data everywhere. Well, what shape is it? S. Like Superman. So light-tailed, right? That's what you'd normally say. S like Superman, light-tailed. Who thinks that's okay? It's a good answer because that's what I've told you so far, right? So, yes, I am tricking you. Yes, yes, yes. But putting that aside, consistent with everything that I've told you, this is S like Superman, should be light-tailed. Okay? All right. Let me show you the histogram. New York before 2001. Right? bimodal. Okay? So what I did, how did I create this data? Really easy. I basically took two normals and just smushed them together. So I created 1,000 normals with mean 5, 1,000 normals with mean 10. So I'm going to have these two normal distributions sitting side by side. Okay, that's how I did it. And there's what I get. Now, there's a link between